Bonjour tout le monde. Donc, mon nom c'est Franco Saliola. Je suis le nouveau directeur du CRM. Hello everybody. My name is Franco Saliola, and I am the new director of the CRM. And I am delighted to be presenting today this year's prize lecture for the CRM-SSC prize. So the CRM-SSC prize in statistics recognizes excellence and accomplishments in research during the first 15 years of a statistical scientist's career following PhD. It is awarded jointly by two organizations, the Centre de Recherche Mathématique, or CRM, which is an internationally recognized research institute in the mathematical sciences that welcomes thousands of visiting researchers each year, and the Statistical Society of Canada, a professional organization dedicated to advancing knowledge and education in statistical science across the country. Together, these institutions promote collaboration, innovation, and the sharing of statistical knowledge within Canada and around the world. This year's laureate is Professor Linglong from the University of Alberta. Professor Kong was born in Henan Province, China, and he studied statistics at Beijing Normal University and Peking University before coming to Canada to complete his PhD at the University of Alberta. After postdoctoral work at Michigan State University and the University of North Carolina at Chapel Hill, we were fortunate enough to have Professor Kong return to the University of Alberta as a faculty member in 2012. Since then, his achievements have been exceptional. He has published over 80 papers in leading journals, mentored dozens of students and postdocs, and served as associate editor for numerous journals, including the Journal of the American Statistical Association, the Annals of Applied Statistics, and the Canadian Journal of Statistics. In recognition of his leadership, he was recently named a Fellow of the American Statistical Association. The 2025 CRM-SSC prize is awarded to Professor Kong for his fundamental contributions to science and to the understanding of complex data through advances in, and it's a long list, quantile regression, high-dimensional statistics, multivariate analysis, statistical machine learning, and applications of statistics to neuroimaging data, personalized medicine, and distributional reinforcement learning, as well as for his outstanding mentorship and editorial service. So please join me in congratulating and welcoming Dr. Linglong Kong, recipient of the 2025 CRM-SSC Prize in Statistics.
Thank you very much for the introduction. I'm glad to be here. I've been for many times. And I even spent my last part to actually in Montreal. I walked by this building many times, but never get to come in. So today, I'm happy to be here and see old friends, old friends and new friends. And so today I'm going to talk about statistical framework for trustworthy learning. And so first, I will have some brief introduction. Then I will share a few of my recent projects. One is differential privacy, one is streaming data on gun learning. Then I will have some closing remarks. So first, what is sort of machine learning? It refers to the models have this property like robustness, can preserve privacy, can provide reliable result, and also is interpretable. And now for those data, for those kind of machine learning methods, especially nowadays in the complex and high dimensional and also evolving environment, how do we deal with those kind of data? How do we guarantee those sort of trustworthy? There are a lot of area making big contributions on this trustworthy machine learning, like computer science, engineering, and so on. And as a statistician or applied mathematician, we can also make great contributions. For example, we can characterize and manage privacy cost trade-off. We can quantify the uncertainty in dynamic and non-stationary setting. And also, especially for our statistician, we can ensure interpretability. And we can principle this model behavior. And statistician, we can provide some fundamental framework for trustworthy machine learning. For example, we can guarantee this, we can have this privacy. And for nowadays, this differential privacy can offer formal risk control for sensitive data. And for our statisticians, this sort of privacy is a long-standing statistical problem, starting with this statistical disclosure control, right? And as statisticians, we can continue to contribute on this part. And the second is the sort of uncertainty quantification. As one of the signatures as statistician, we do a lot of inference. We do a lot like process tests, constant interval, and so on. We provide a lot of tools to quantify those uncertainties. And the third one is the robust generalization, and a lot of statistical tools, and especially in robust data analysis, we can provide tools to deal with the sort of out-of-sample performance or out-of-domain performance. And this is very important for the generalization. And the last one is also very important one is model interpretability. This is one of the emphasized area for our statistics. For example, we can use the tool for inference function, counterfactual analysis, and post-selection inference, and so on, to make this a transparent connection between model output and the input data. So the key message here is our statistician, our statistic can provide theoretical mechanisms to quantify the control and to model the behavior and to forming the bedrock of this trustworthy machine learning. And in this presentation, I will share two projects we did recently. The first one is Gaussian Differential Privacy on Riemannian manifolds. This was done by a recently graduated PhD student, Yang Di, and a postdoc, Xiao Tian, and PhD student, Yi and Lei. Yi Riemannian is a faculty member at York University. Lei is a faculty member at the University of Manitoba, and my colleague there. So first, let's have a look at what's this differential privacy. And in general, this differential private algorithm, they achieve this privacy to ensure that any individual record will not have a huge impact on the outcome, whether this individual is in the state or not. The result won't change very much. And then the scale of the impact can be as this individual record can be controlled by privacy parameters. For example, this Epsilon delta dp and this Epsilon delta are those privacy parameters. The smaller parameter means more private. But in reality, we usually need makes the trade-off between privacy and utility. To protect privacy, you can just give some data totally non-use, but that's not what we want. We want privacy. We want to protect privacy. Meanwhile, we want to provide data that is useful so that we can do our analysis. So this is a sort of a data utility and the data privacy trade-off. And with nowadays the data collection, we also want to look at those nonlinear data situations. In particular, for example, if our data are located in a Riemannian manifold, and how do we do it? And we want really sort of M-valued statistical summary statistics. Meanwhile, we also want to maintain this data utility. And the data privacy mechanisms here we are using is this Gaussian differential privacy. Before we go to detail, let's first look at what's this differential privacy. We have a data releasing mechanism. We said, okay, it's Epsilon delta dp if it satisfies this condition. It satisfies the probability, this probability, MD in A less than E epsilon, the probability MD prime in A plus delta. And what's this D and D prime? D and D prime, they are, the data set only have one record different, only have one record different. And if that is 0, then we say is Epsilon dp. Epsilon dp usually can be very easily achieved by injecting Laplace noise. Laplace noise. For example, we can have a Laplace noise B equals delta over epsilon. Delta usually is the sensitivity of the query result. Now, this epsilon delta dp actually is a well-defined concept, and in any measured space, it can be readily extended to any Riemannian manifold. And there are actually some work to extend these Laplace mechanisms to the Riemannian manifold. For example, in the Ricci 2021 paper, we have these Riemannian Laplace mechanisms. And we also have some situation to extend the Gaussian mechanism to achieve Epsilon delta dp for some particular case. For example, the space of symmetric positive definite matrix with log Euclidean matrix. And this is in particular useful because the space of symmetric positive definite matrix usually is this covariance matrix. So for statistics, it's very useful. Now, this is the Epsilon delta dp. There are many other possible different privacy definitions. And in particular, recently we have this Gaussian differential privacy. We call it GDP. The GDP is very useful, and but they work to extend this GDP to nonlinear data, and it's limited. And in the case of Epsilon delta dp, in the GTP situation, there's no existing one. So our target is we want to extend this GTP concept to general Riemannian manifold, so that by developing this Riemannian Gaussian mechanism. Now, what is GDP? The GDP actually is 2022. This is a pivot family of this FDP, and it relates the epsilon dp from a hypothesis testing viewpoint. And previously, the epsilon delta dp is introduced by computer scientists, and the definition is a little bit challenging to understand. Here, this GDP, on the other hand, it's looking from this hypothesis test, and it's very easy to integrate. In particular, what's GDP? And we have a mechanism M, which said it's set by mu GDP. mu Gaussian differential privacy or mu GDP if this MD prime greater than G mu for all neighborhood data set. And this G mu is Tn01 and N mu 1. So G mu is a test statistic based on testing hypothesis, standard normal, and another normal distribution with mu. So this T actually is the optimal trade-off function between type 1 and type 2 error. So informally, this mu GDP says it's harder to distinguish D from D prime than distinguish between standard normal distribution and another normal distribution with mean mu and variance 1. So this GDP actually can be interpreted in this way. And this is much easier to understand than the previous Gibson therapy. And we do a lot of hypothesis tests. So this GDP, the privacy preserving, we compare it with a hypothesis test to distinguish a standard normal distribution and another normal distribution, the mean mu and the variance 1. So of course, a smaller value of mu provides stronger privacy and guarantee. If mu is small, then it's harder to distinguish between standard normal and this normal mu 1. And for this GDP, it possesses a lot of good property. And here we list some. One is all hypothesis testing-based privacy definition convert to the guarantee of mu GDP is the limit of composition. This is something similar in the theorem. And compared to epsilon delta dp, GDP has this superior composition and subsampling. This is another reason why this mu GDP nowadays is quite popular. Now, with this, a lot of and how do we achieve GDP? To achieve GDP, it's actually also very easy. We can use additive Gaussian noise. For epsilon delta dp, we can use the Laplace noise. And so for GDP, we can use this Gaussian noise. And we actually have the following proposition. We can convert this GDP to this infinite fraction of epsilon delta dp from this position. And this is very important to make the connection between the GDP and epsilon delta. Why it's important? Because epsilon delta dp came first. We have a lot of differential privacy mechanisms. They get this private preserved data already. They actually use epsilon delta dp. Now, if you want to use mu GDP, then this proposition can make sense. We actually have a previous work to fully characterize epsilon delta dp. When epsilon delta dp is mu GDP, and if it's not a mu GDP, then how we convert it to mu GDP. It's another work we did. Now, let's look at this GDP. It's very powerful, very popular, very useful, but this sort of hypothesis testing definition is very challenging, very hard to work on manifold. However, because we have this this property, then we can start work on epsilon delta dp. Then we go back to a mu GDP because this epsilon delta dp is well defined on this Riemannian manifold, and through this connection, we can get this mu GDP manifold. Now, in particular, how do we do this mu GDP on manifold? We first extend this Gaussian distribution to manifold. We have this Riemannian Gaussian distribution have the following form, and this form, as you can see, is quite similar to this Gaussian distribution in Euclidean space. But we have to look at this in Euclidean space. We have this sort of mean and variance, or we have location and variance. In this Riemannian Gaussian distribution case, we actually have this footprint eta. And also we have this read parameter sigma, And we also have this Z sigma, which is the normalization parameter. In order to have this Riemannian Gaussian distribution well defined, we need this constant normalization constant that need sigma to be finite. And this is not much issue because we take it to compact manifold or any manifold with lower bounded sectional curvature. And if we restrict the manifold on this either situation, then this would be finite. Then this Riemannian Gaussian distribution will be well. However, there's another issue for this Riemannian Gaussian distribution. It's this normalization constant that is sigma. It also depends on this location parameter. This is going to cause some issue. As we call in this Euclidean space, for the Gaussian distribution, this normalization parameter actually doesn't depend on this location parameter. Well, for manifold, this Riemannian Gaussian distribution actually depends on this location parameter. And this will cause some issue later on when we compute the density ratio In order to achieve this Gaussian differential privacy, we can add this Riemannian Gaussian noise with footprint FD and read sigma so that we can have this mu GDP. And how to determine those parameter like footprint FD and sigma and read parameter sigma, they have to satisfy this condition. And so in order to have this Riemannian Gaussian distribution to have this GDP, and at previous we said we want the normalization parameter to be finite. So we can receive the manifold with a lower boundary curvature that can be solved. However, with this inequality one, it's very hard to build the connection between the parameter C and the privacy budget mu. Okay. We say, okay, if your Riemannian Gaussian distribution satisfies those conditions, then it will be a mu GDP. Okay, but then you need to find what's the mu. So you need to make the connection for certain rate sigma, and then what's the corresponding mu. You need to make the, but it's very challenging here. Now we go back to the situation, and we start with one simple Riemannian manifold. We start on S1, and we look at this S1. We look at this S1, and for the Riemannian Gaussian distribution, we find it's mu GDP if and if mu satisfies the following condition, satisfy those following condition. Satisfy this H sigma epsilon dot less than or equal to dot mu epsilon, and this H sigma epsilon delta is this one, and we have a constant C delta is this one. And even though it's a little bit complicated format, but it's doable, we actually can find this view. So here is the algorithm, and we have this on unit circle, and we have the sensitive delta, and we have rate sigma for the remaining Gaussian mechanisms. Then we can find this mu through this algorithm, and we split this epsilon into n epsilon candidate. Then we can compute this mu epsilon, and then satisfy this condition. Then we find the maximum one. We find the maximum one. It's approximate, but we can actually find this mu. At the beginning, we stopped here. We have this, theoretically we make the connection and we get one example. But of course, the reviewer are not happy because this unit circle is too simple, and they want us to have more complicated, non-trivial example. And it took us some time to get it. Now let's recall what's the challenge. What's the challenge? Why we cannot get the general result? The key thing is this inequality. It's very hard to evaluate. And so we think about, is there any way to simplify this inequality one? There are two challenging parts in this inequality one. One is we need to evaluate these two integrations. The other one is we need to find the supra. We need to find the supra. Okay. And in order to do that, we think maybe we can do this for these two integrations. Maybe we can use this sort of Markov tree, MCMC. But in order to use this MCMC, we need to evaluate the density ratio. And this density ratio actually related to this location parameter. And it's not possible to implement. And like I said, the other one is after you evaluate these two integrations, you still need to find the supra. Then we thought, okay, let's go back. Let's go back to RD situation. We can get any hint. And for RD situation, for the Euclidean case, okay, this set A actually relates to a box. And this inequality one reduced to this one, And then this Riemannian Gaussian mechanism relates to the regular Gaussian mechanism as the initial definition. This actually gave us some hint, whether we can work on that so that this integration can be easily calculated. So we actually checked all different manifolds. We found all these homogeneous manifold. This ZE sigma actually doesn't depend on this location parameter eta. Therefore, this set A can be reduced to this one, And that's one thing we use. We reduce this to homogeneous manifold. Now, how do we deal with this super. We actually also able to find a non-trivial case. We have if the manifold have constant curvature, then we have the following result. And we have the following result. This E1, E2, as long as this distance between E1, E2, and E1 prime, E2 prime are the same, then this will be true. This will be true. So with these two property, if the manifold is a homogeneous manifold, if the manifold have this constant curvature, then we are able to evaluate those inequality, evaluate this inequality, and we can ignore the super. We can get rid of super. We can simplify the set, and therefore we can use MC to approximate the integration. And so that's a general case, non-trivial case for these Gaussian mechanisms. We can have the result for manifold with constant curvature and homogeneous manifold in these two conditions. We can have this this algorithm, this MC algorithm, so that we can compute the privacy parameter mu. Okay. Now let's look at so at the second summation, we provide this result, a non-trivial case. We have this F1 unit circle as a special case. We have this homogeneous manifold with constant curvature as a general case, and then the paper was accepted. And here is a simulation on this subfield, and we work on this H2, and we have this. We look at the private fractured mean. We implement two methods. One is we have privatized mean by drawing from this Gaussian distribution. The privacy budget mu is using the previous algorithm. The next one, we convert mu GDP to equivalent infinite GP, and then we generate privatized mean X bar Laplace using this sampling from Riemannian Laplace distribution. Then we compare these two methods. In general, this is our method. This is sort of a method circulate the Gaussian mechanism. So here is the result. The red one is our method, and the blue one is the comparison method. As you can see, our Gaussian mechanism actually achieve better utility, especially with smaller privacy budget. With the larger mu, the gain in utility is less pronounced. And why? Because one obvious reason is that there are much fewer perturbations with larger mu for both approach. So the difference is subtle. Another reason is the algorithm have a tendency to overestimate mu with smaller signal. Okay, and in practice, actually, if the mu is large, then the privacy protection actually is not that much. Because you think about if you are to distinguish a standard normal distribution with a normal distribution with mean 4, and then it's very easy to distinguish it. It's much easier, right? So the privacy protection is less. Okay. So this is the project on generalize the real GDP, which is a very popular privacy mechanism, to the nonlinear data, which is the manifold situation. Now, let's look at another project. This is published in Journal of Mathematics and Statistical Inference for small quantile regression with 3D data. Basically, it's a kind of online learning. And the first author, Ji Han, and the second author, Zhou Lu, were all postdoc, and Bei is my colleague. So, for quantile regression, we basically want to use this minimize using this quantile check log function. And here, for streaming data, it's a little bit different. We have actually have the data is coming back, and the data is coming back. And let's say here we have a B batch data. And then once we get we start with first batch of data that we get an estimate. Then after we get the estimate, due to various reasons, we may not want to store the data. Okay. We may need to discard the data. And now the first thing is, when the next batch data is coming, how do we update our estimate? And whether we are able to find a method so that we can effectively update our estimate as good as we have all the data, maybe. And that's all. That's the goal we want to achieve. That's the goal. So for quantile regression, we all know, because it's this check log. Here we actually have this indicator part, and it's not smooth. It can cause a lot of problems, theoretically, and also to computation. So to deal with this, the reason is it's not smooth. The quantile function is not smooth. And a straightforward method to deal with it is, if it's not smooth, then we smooth it. And this actually is what we did in the past. And but how to smooth it? There are many different ways. For example, we can do the kernel smoothing. Okay, kernel smoothing. And kernel smoothing, and thirdly, we have this fourth order theorem. And then we can do this gradient descent and so on. There are also another smoothing method, which is called the convolution type smoothing method. Because in practice, sometimes only first derivative available may not be good enough, especially when you want to deal with quantify the uncertainty to do the inference. You want this second order information, right? And maybe you want the second derivative. In the literature, we actually have this convolution type smooth method, and we smooth this empirical distribution through this convolution type smooth method. The advantage of this smooth method is we are not only have this fourth order derivative exists, but also is twice continuous differential, so that we would have 3D, and also this Hessian matrix also have Hessian matrix. Therefore, we can have a lot of choose ways to develop this, let's say, result. So in this project, we actually use this convolution type smooth method. Now, how do we use this? Let's first look at this low dimensional situation. For low dimensional situation, we actually look at, we start with this simple scenario. We have two batches, batch D1 and D2. Okay. For D1, once we have the first batch, we can use the data to calculate to get an estimate, let's say a mu cubed H1 and 1. We get the first estimate. And then we can get rid of data. We have the second batch of data. When the second batch of data come, how do we update our parameter? The way to do it is we actually look at this sort of Taylor expansion of this loss function, and we can measure of this result by noticing the first the difference between this first batch true value and the second batch true value. We're actually using this Taylor expansion. For this higher order, it can be ignored. As a result, we have this sort of renewed smooth QR estimate. This data with first batch data and the second batch data, they should satisfy this condition and this condition. What does this condition mean? That means our estimate actually the D2 is the second batch of data, and we have D2 data available. But for the first batch of data, we only need the estimate from data from the first batch of data, and also the second order information from the first batch of data. So we don't need all the data. We only need the estimate and the estimation. And then we can get this updated estimate. We put this all together, we will have this one. For this low-dimensional online situation, we have this. We first have this B-1 batch of data, so we get the estimate up to B-1. Then when the B batch of data come, we only need to minimize this one, and this is coming from the B batch data, and those coming from the previous estimate beta and some summary statistics, second order information related to the Hess matrix of the estimate. So through this, we essentially only need current batch data, some summary statistics, then we can get the estimate of we can get the updated estimate. Okay, this is for low dimensional situation. For high dimensional data, the key thing is to do sort of a variable selection or feature selection. And one easy way to do it is we just add this L1 panel. Indeed, we can do that. And we can conduct a sort of L1 penalization. We penalize those parameter beta. And this part is from this low dimensional situation. We only need current batch of data, the previous summary statistics. And then we add this L1 panel. But we actually have some issue here. Okay. In non-streaming data situation, we can choose this penalization parameter through cross-validation, right? Through cross-validation. But how do we choose lambda b here? Because the data is coming on batch, and we don't have previous data. The way to do it is we have this adaptive regularized parameter selection. We call data is called rolling original recalibration. Rolling original recalibration. The key idea here is we actually have a candidate lambda. We have a candidate lambda. Okay. Let's say we have 10 lambda. And for the 10 lambda, for each batch of data, and we do this optimization. We do this optimization. Okay. We do this optimization. And for all these lambda, I say if we have 10 lambda, then we do 10 updates. If we have a 20 lambda, we do 20 updates. Then among these 20 updates, we choose the best. Okay. So this is called rolling original recalibration. This solves the choosing of lambda problem, but we still have another problem if we want to infer. Remember, we want to do this trustworthy machine learning, and the uncertainty quantification is very important. And we want to not only to get that, we also want to do inference. Okay. But for lasso estimate, we all know in most of situations it's sometimes not even consistent, and it's not a good estimate to do inference about it. So the key, the reason is it's actually get some bad. So how to deal with that? We actually have this debiased lasso estimate. And so in order to deal with non-trackable limiting distribution, we actually are using this this technique to debug the lasso estimate so that we get the consistent estimate, and this consistent estimate get good limiting distribution. And the key thing is to get this inverse matrix of the Hessian matrix. The inverse matrix of the Hessian. Now, eventually, our estimate, debiased estimate, coming from this file, coming from the original smooth update, and with two adjustments. And one is sort of a debiased term to correct this outline bias to correct this bias. This is generated from this online generalization. The other one is error correction. This error correction is due to the approximation of the information matrix. So that's these two terms, and we need these two terms correct. Now, as we did the two term correction, we need to go back to see our sort of renewable process, whether it still works or not. Remember, in low dimensional case, we need have the summary statistic estimate of data and its Hessian matrix. We have the current value of data, then we can update. And because for high dimensional situation, we need do variable selection. So we need to lambda. Therefore, we have this rolling and recalibration. For different lambda, we needed to do all this, and that's one added. And then we need to debug, and we need at least two terms, And the burden to at least two terms is we need remember more summary statistic. Here we need to remember H1B, H2B, and also this Q should be. And at the same time, we need this current value. So that's the whole procedure for methodology. And then we look at this theoretical property. we look at for low dimensional case. For low dimensional case, it's relatively easy, and we have this consistency. We have this normality, and for high dimensional situation, it's a little bit challenging. We first have this sort of consistency, okay, and in terms of L1 norm, and also L2 norm, this consistency. And the next is also very important is whether we are able to have this trustful limiting distribution so that we can do inference. In order to have the limiting distribution, we first need to look at how good is our estimate for the information matrix. And here is the result to look at how good is our information matrix estimate. And based on this, we actually have this sort of asymptotic distribution or limiting distribution for high dimensional for high dimensional set. And in particular, the limiting distribution can be decomposed into two parts. One is ZT, this part. The other one is WT. WT is a 10 to 0 in which, and this ZT actually is a summation in terms of bad state, and we can estimate the workings of these parts. So this ZT, and therefore we can have this sort of theoretical result, this possible limiting distribution for high dimensional situation. Now, let's look at the simulation study. For simulation study, we did it for low dimensional situation and also high dimensional situation. We did it for stochastic model and also heteroscedastic model. And we did for fixed batch size or fixed total sample size. For the evaluation criteria, we use the average absolute bias and the average estimated standard error, individual standard error, coverage probability, average constant interval length, and so on. And here, I only present this homoscale model theory. And the simulation result actually support the claim that for this online situation, the result is as good as this offline situation. So that means in low dimensional case, even though the data is coming in batch, we don't store all the data. We only store some summary statistic. We can still get the estimate as good as we use all the data. And we also look at one new data analysis. We have this so by-sharing demanding data, and this data was collected from December 2017 to November 2018. The response variable is the count of rainfall by relative at each hour. And we currently have 73 batch of data. And the total sample size is 8,750. We have some potential factors like our temperature, humidity, wind speed, visibility, and so on. And here I just list result. We are not only able to get the estimate, we are also be able to get this confidence interval to get the confidence, or this, in this case, confidence factor. So this is the second project I want to share with you. As a summary, so here I use two projects to demonstrate, as a certification as applied mathematician, we can indeed compute this trustworthy machine learning, and our statistician or applied mathematician can play significant role in this nowadays sort of trustworthy artificial intelligence. And in particular, we look at this differential privacy project. We expect the GDP to the manifold situation, and also we look at the streaming data estimate and the inference estimate. And for this, to extend this GDP to Riemannian manifold, the key thing is to solve this this integration depends on the location, and also to solve how to get the super part. And that's the key thing for this GDP. For robust online learning, the key thing is how do we utilize current data, and how do we aggregate the historical data? How do we integrate them all together? So, as I said, our statistician actually can, compute a lot for this sort of trustworthy machine learning in some different fields like probability formulation, accuracy quantification, robustness and generalization, and especially the last part, interpretability. That's one key training component for our statistician. And so for my lab, we actually working on bridge this statistics and the trustworthy machine learning, trying to use statistics to help trustworthy machine learning. And on the other hand, we use some tools from trustworthy AI to help our statistical modeling. For example, nowadays we can use large language model and to help us to do uncertainty quantification, to do some in-context learning and so on. Here are some topics we're working on in our lab. In particular, high-dimensional data, neural image data, function data analysis, privacy-preserving statistics, fair machine learning, online learning, reinforcement learning, and so on. I think that's all for my talk. Thank you.
Any questions?
I'm not sure if I understand why we cannot use cross validation for the second project. So when you're on batch 1, you could use cross validation to estimate the lambda, right? For the first one.
For batch 1, yes.
And then for batch 2, the only thing you need, you just need the estimates from batch 1, the Hessian from batch 1. So you could just do the split the sample of batch 2 only. No?
Well, technically, yes, we can see it. It also depends on the batch size. And,
oh, yes. Okay.
And this, you get only that many new data. You want to train your model instead of choose a parameter. And in that way, that will be more efficient.
Okay, so this is in a case where you have small, but you have few batches, no, in your example. So then you'll be big, no? Not.
So the batch size can be limited.
Okay.
If your batch size, let's say for each batch, if the number of sample is very large, then basically you don't have any problem.
Yeah, sure. Okay.
And but if the batch size is not that large, then you want to say that sample to do estimation instead of to choose parameter.
Are there any other questions from the hall? Oh, Nick.
In the first project, when you talked about using MCMC to approximate those two integrals, I don't really understand why you need the ratio of the two densities, since the densities, I think, was p eta 1 and p eta 2. they appear separate integrals.
Because you need these, when you do the sampling, you have a sort of a reject. And when you do the reject, you need to look at the ratio to decide whether you reject or not.
Okay, but isn't the ratio of p eta of x and p eta of y something like that? The argument, not the problem. The sign.
The ratio actually depends on the location parameter. That's the challenging part. Yeah, because the density, like the regular Gaussian distribution, okay, you can get rid of the ratio, get rid of the location, right? Because exponential, right? And but for that one, it really depends on the parameter of the location parameter. You cannot get rid of that location.
Are there any other questions? Maybe a question from online? If so, just unmute yourself. Doesn't seem like there's any online questions. So we do have a reception afterwards, so we can continue the discussion at the reception. Thank you, everybody.